So today we will be solving Major 22 paper 42 question 1. So the first part is asking you to define gravitational potential at a point. So gravitational potential is basically, or let's just write directly, it is the work done in bringing unit mass from infinity to a point, right? So it is work done per unit mass. So there are 2 points to it, per unit mass and in bringing the mass from infinity to a point. Mass from infinity to a point. Right, so that's it for our first part. Okay, then they're saying, starting with the equation for the gravitational potential due to a point mass, show that the gravitational potential energy EP of a point mass m at a distance r from another point mass m is given by, okay, so basically you're given the equation of potential energy and they're asking you that how is it derived from the equation of potential, right? So they had given you the equation of potential energy and they're talking about how did you get this from the equation of gravitational potential into a point mass. So if we talk about it, we know that basically potential energy is equal to what? It's equal to potential due to a point mass into the mass, right? So it's equal to potential into the mass, right? So if I'm going to write it in terms of our formula, then I'm going to get E equal to our potential. So the equation of our potential is Gm upon R, right? So Gm upon R. So this is for potential and then into our mass, which is N. And potential equation also has it at that sign, right? So when I'm gonna do this, I'm gonna get, so the mass small, I'm gonna get E equal to minus Jm m upon R. That's how we get the equation. Oh, right? This is your equation for potential energy. Moving on, you're saying figure 1.1 shows the path of a comet of mass 2.20 into 10 to the power of 14 kg. So this is the comet and it's moving at this point. It has a particular speed which is given as 34.1 kilometer per second. And we're saying that it's passing around the star of mass, distant mass, right? And then they're also saying that the comet is 8.44 into 10 to the power 11 meters from the center of the star and it's moving at a speed of 34.1 kilometer per second. So this information is for point X, and then they have also provided information for point Y, where they've given you the distance, right? So what are they asking? Both the comet and the star can be considered as point masses at their centers. Calculate the magnitude of the change in the gravitational potential energy of the comet as it moves from position X to Y. Okay, so if we talk about this, we know that change in potential energy, we're gonna subtract potentials at point X and point Y, right? So if I do that, I'm gonna get, so we know that minus sign comes, minus G M upon R minus, and then another minus to it, minus R, right? So if I further simplify it, I'm gonna get Gm M upon R plus Gm M upon R, right? So what I can do is I can take out my Gm common, Gmm common actually, right? And now what I'm left in the bracket is minus 1 upon r plus 1 upon r. 1 upon r, right? And I can also write it as Pm and 1 upon r, sorry, 1 upon r minus 1 upon r, right? And then now you can finally substitute in the values, right? So my values are gonna be G is constant, 6.67 into 10 to the power minus 11, so that stays the same. And then mass of the comet and mass of a star. So mass of the star is 1.99 into 10 to the power 30. So let me just input that to 1.99 into 10 to the power 30. And your mass of the star is 0.99 and mass of the comet is 2.20 into 10 to the power 40. 2.20 into again 10 to the power 40. And then in bracket we have the radius, right? So that is what is at point x. At point x we have given, okay, so at y it's this, yes. So it's 8.449 to the power 11, and then the other one is 6.38. So we're going to write the smaller value first, right? Because when we're going to divide that by 1, we're going to get a bigger value, right? So that is why the smaller distance first. 6.38 into 10 to the power 10 it is, and then minus 1 upon 8.44 into 10 to the power 11.44. 8.44 into 10 to the power 11. Right? So that's pretty much it. And when we're going to solve this, we're going to get the answer 4.23 into 10 to the power 23. Right? So this is our answer. And of course, unit is always Joule for energy. Right? So this is it for this part. Now let's move on. Okay, say that the reason whether the change in gravitational potential energy is an increase or a decrease. Okay, so if we talk about this, you know that basically every surface, like every planet or something, is going to have its own gravitational force, right? So, which is basically an attractive force, right? So, if the comet is moving away from it, that means that it's doing work against that attractive force, right? So, when it's going to do work against the attractive force, the gravitational potential energy is going to decrease, right? Why? Because it's going to convert into kinetic energy because it has to move away, right? So that is the idea gonna explain it. So gravitational field strength is attractive force as the comet is moving away, doing work against it, and, and GPE, which is your gravitational potential energy, is converting to KE. Right, you can write the full form in the answer. Right, so that's our answer. Okay, so for this part, we're going to use the same idea that you know that GPE is going to convert to KE, right? and we already know, and it's basically the change in gravitational potential energy that would be equal to changing 4.23 into 10 to the power 23, right? So we're going to equate this to change in kinetic energy, right? So there we go. And we know that it's equal to half mv square. And because we're going for change, we'll subtract initial velocity from final velocity, right? So if you look at the mass of the comet, it is 2.20 into 10 to the power 14. So into 2.20 into 10 to the power 14, that is our mass, and our change in velocity is the final minus initial, right? So let's take a look again. So this will be the final point, right, which we don't know. And this is the initial point, which is 34.1, right? So final, I'm denoting it with F at the moment, minus initial, which is 34.1, and this is in 4 meters per second. According to SI unit, I will have to multiply it with 1000 to convert to meters per second, right? So when I'm going to solve this, I'm going to get the value of my F as 7,800. And this again, is in meters per second because that's how I solve by SI units, right? So I'm going to convert that to kilometers per second. And for that, I'm going to divide by 1000, right? So divided by 1000. And that means my answer will come as 70.8 kilometers per second, right? So that is my answer for this part. Next, they're asking, a second comet passes point X with the same speed as a comet in B and traveling in the same direction. This comet is gradually losing mass. The mass of this comet when it passes point X is the same as the mass of the comet in B, but it's still losing mass, right? And then they're saying, suggest for the reason how the path of the second comet compares with the path shown in figure 1.1. So we know that the path is dependent on what? It's dependent on two energies which the whole question was based on, and that is potential energy and kinetic energy. So the point is that if it's losing mass, that is going to impact both kinetic energy and potential energy, right? So at the end of the day, the path is not going to differ, it's going to be the same, right? So that is the answer to this part, and I'm going to write it here. So change in mass is going to impact both potential energy and kinetic energy, so they change. So no change, right? So that's it for this one.